is equal to charge times mole, or rather that K is equal to moles times charge present in this case. Now, I want us to use this K and make it X. That's what we call I just gave this particular thing so that calculation becomes very easy. Just follow up. You understand that this is the simplest way to do it. Because second law, people have demanded I do video on that, both teachers and students. But thank God we are here. I've made time out to give you this. I want to use this K to make it X. And this formula, I call it majestic factor or X factor. We're going to be using... We are here again, the easy world of science. Today I'm going to handle a nightmare, a topic or a law that students find difficult. And that is second law of Faraday. I tell you what, it is not difficult as you think. Let us see how we will simplify it today. I'm going to handle second microfaraday's law of electrolysis, and most importantly, its calculations. So, first law, I've treated that in this channel, so look it up and watch. Enjoy. Remember, I'm here to serve you, and don't forget to share this video. Don't forget to spread the light. Expand this community, please. We cannot do without you. We work every day for your academic success, so work every day for the success of this channel. God bless you. Now, according to Michael Faraday, the second law, according to him, he stated that I want to put it in his original form before we now come to the modification. He said that the amount of chemical change that is produced in different substances when they are supplied with fixed quantity of electricity is directly proportional to the electrochemical equivalent of the substances. The amount of chemical change produced in different substances by passing fixed quantity of electricity through them is directly proportional to the electrochemical equivalent of the substances. In a more mature way, we say that the mass, or you say the quantity of electricity or the charge required, to liberate a mass M is given as Q equals Fmz over M is quantity for second law, whereby F is Faraday constant, which is 96,500. M is the mass. Z is the charge present on the element. Then this is the ionic mass of the element in question. But this is more advanced. But according to Michael Faraday, it says that the amount of chemical change produced is proportional to the electrochemical equivalent present if they are all supplied with the same quantity of electricity. So, in this case, let me state it in a simpler modern way for you to understand. The second law states that when the same quantity of electricity, but here they talk about charge because the charge here is still the quantity, when the same quantity of electricity is passed through different electrolytes connected in series, that the number of moles of the elements discharged is inversely proportional to the charges present on the ions of that element. This will enable you to understand it very well. I take it again, that when the same quantity of electricity is passed through different electrolytes, that the amount, or rather the moles of the elements discharged at the electrodes, of course, is inversely proportional to the charges present on the ions of that element, which means ions with higher charge will consume, ions with higher charge, when we say inversely proportional, of course, ions with higher charge will consume more quantity. The second law is trying to tell you that ions with higher charge, the lesser moles of them will be discharged. Then ions with lower charges, the higher moles of them will be discharged. Okay, here we're talking about Faraday's second law. So, having stated that, I'm trying to tell you that we are comparing moles and charge. and they are inversely proportional. So it means, in my own way, I tell you that moles of the element discharged is what? Inversely proportional to the charge. And inverse proportion is 1 over. Which means that if I should do this mathematically, although it's not my business, you have to introduce K in that case. So there should be a constant, which is actually the same quantity of electricity. So in that case, we might say that moles is equal to K over charge. So that K is equal to charge times moles. Exactly. K is equal to charge times mole, or rather that K is equal to moles times charge present in this case. Now, I want us to use this K and make it X. That's what we call I just gave this particular thing so that calculation becomes very easy. Just follow up. You understand that this is the simplest way to do it. Because second law, people have demanded I do video on that, both teachers and students. But thank God we are here. I've made time out to give you this. I want to use this K to make it X. And this formula, I call it majestic factor or X factor. We're going to be using X factor here, whereby simple, you can now just say that X is equal to just what we just say here, moles times charge. But here, we want to, there are different charges. There are elements with, common ones we meet in our exams are those with +1, like sodium, those with +2, like copper, those with +3, like aluminium. So, those of them now, these are the common ones we will meet. Please, even when the charge is minus, it is still applied, because what matters is that number, not even the magnitude. Like the plus, the minus doesn't matter here. So what I mean, if you see a charge like -1, we'll still take 1 in this case. So permit me in the X factor, you just say that X, remember, is a constant now. That's what I used to replace this. X is equal to, we take for this, number of moles of univalent. When you say univalent, it means that the charge is 1. So you say times 1. Remember, moles times charge. Uni, 1. The same X, which is a constant, is also equal to number of moles of what? Divalent, still times what? 2. See this first thing? Remember that this X is K, is a constant, but I want to use X that we know very well. The same constant is equal to number of moles of trivalent, such as aluminium, times the charge on aluminium, which is 3. So if you have an ion that also has +4, you can equally solve. But to prove to you what this law is talking about is that if you have more charge in you, the lesser mole of you will be produced. Simple. Let's go on and see this. Okay, let's go with Ag +1, copper 2+, and aluminium 3+. You see, the charges in ascending order is +1, +2, and +3. Then, can we take the inverse? Inverse of 1 is 1 over 1, which is 1. Remember, the inverse, this is charge. Let's now see mole. They say that mole is inversely proportional to charge. So what's the inverse of 1? 1 over 1, which means 1 mole. We are taking a look at 1 mole. It means that if 1 mole of this copper silver is produced, how many moles of copper will be produced? You take the inverse of this charge, which is 1 over 2. The inverse of 3 is 1 over 3. Note this, any number that is standing is a whole number and is over 1. If you have 3, it means 3 over 1. If you have 4, it means 4 over 1. When I say inverse, you change it. But you don't usually put that 1 because 2 over 1 is still 3. So when I say inverse of 3, you just take this 1 up and bring this 3 down. And that's why I have 1 over 3 here. Now, if you press your calculator, this is 1. This is actually, you want to know the moles, 1 mole. This is 1 over 2 is 0.5. Then here it will be, calculator department, get me 1 over 3
times what?
Plus 1 over 3. Okay, 1 over 3 only.
0.333.
Okay, yeah. 0.33. Continuous. So if you check now, let's see charge and mole, how they are moving. See when charge is 1, 2, 3, that is increase, is getting higher. But see their mole, 1, 0.5 and 0.3 is decreasing. So it shows that moles and charge are inverse. So meaning if you have higher charge, the lesser number of you that will be discharged. In that case, let's now represent this with a number, assuming that 12 moles of silver was discharged. Can someone find the number of moles of copper that were discharged? Yes. We just say, in that case, take note, our x here is a constant which is for plus 1. You take it. Take it that this is a constant and it's for elements that have plus 1 charge. So in this case, if I give you here as 12, it means that my x is 12. But not just minding, what does it mean? You now say 1, you go back to know the number of moles of copper discharged. You come back here. Copper is divalent. You use this formula. X is equal to N over this over this. So remember, this is mole, not mass, please. Even if you substitute it here, that's why I told you that X is this. Or you put this 12 here. What will it be? 12 is equal to, what's the number of moles on silver? 1 times 1, which is still 12. That's why I told you now we have solved our X, and our X is 12. It's usually for the monovalent. So you now put the same 12 here because it's still X is a constant. And we are looking for copper. What do? You just say the same 12 is equal to number of moles of the divalent. That's what we are looking for. If you don't know the number of moles of this, therefore it means number of what? Moles of copper times what? 2. Make this one subject to the formula. Divide both sides by 2. Divide by 2. Divide by 2. So what do we have? The number of moles of copper is equal to 12 over 2, which is 6. So for trivalent, you do the same thing. It should now be automatically x is equal to, and our x is 12, is equal to number of moles of trivalent times 3. So what do you do here? You still do the subject of the formula, divide by 3, divide by 3, cancel, cancel. So what do you have? 12 over 3, which will give you 4. So it means that if 12 moles of silver is discharged, 6 moles of copper will be discharged, and 4 moles of aluminium will be discharged. So this is a real number, no longer point. You see, 12, 6, 4 is decreased, but the charge is plus 2, plus 1, plus 2, plus 3 is increasing. So that is it. Use this X factor in that case. So let us take many examples. I'll just give you examples and you will get mastered while solving. Example 1 here is a given quantity of electricity discharged, a given quantity of electricity discharged 0.4 moles of copper. Calculate the mass of silver that will be discharged by the same quantity of electricity, or by the same electricity. So in brackets you'll be given that silver is 108 and copper is 64 or 63.5, depending on what the examiner wants you to use. They might give you Faraday to confuse you, just to know if you know what they're doing. Now, if you are faced with this question, a given quantity of electricity discharged 0.4 moles of copper, calculate the mass of silver that will be discharged by the same quantity of electricity. This is second Faraday law. How do you know it in exam? If you see 2 elements mentioned in one question with a figure given, know you that they are asking you second law. In the first law, just watch it, they give you the acronym, every cheat you need. They only mention 1 element, they may call it X. But when 2 elements are compared, 3 are compared, it's talking about second Faraday's law. Your question, first, the one that was given, the given mole is for copper. And you go to our formula, which says that X is equal to number of moles of divalence times 2. Solution. So what do you say? Because we are talking about giving ion. The ion given was copper. meaning the number of moles I was given about is copper. Then you lift our formula, and copper is plus 2. X is equal to number of moles of copper times 2. And you have discovered this factor we are talking about. Number of moles of copper from the question is 0.4. So our X is 0.4 times 2, which is automatically 0.8. This 0.8 is our X factor. We have gotten the X, and I call this method X factor. Then you keep your X and go to the one they ask you to calculate for. Calculated for is, what's the ion calculated for? They tell you to calculate silver. You write it, silver. What's the charge on silver? Plus 1. You go to our formula, which says the same X is equal to monovalent, because the charge on silver is monovalent, is equal to monovalent times 1. Then X has been discovered to be 0.8 from the question. It becomes now 0.8 is equal to monovalent, which you don't know, times 1. So in that case, you will make the monovalent here subject of the formula, and that will give you the correct thing. So what will it be? Divide by 1. Divide by 1. And it shows that if 0.4 moles of copper is discharged, that 0.8 moles of silver will be discharged. But the question says the mass, calculate the mass. Remember, in this law, you are working with moles and not mass. You must move from mole to mass. The law did not say that the mass of the element discharged is inversely proportional to the charge. No, it says that the number of moles of the elements discharged is inversely proportional. So if they give you mass, convert that mass to mole and then use it to obey the law I've taught you. Bring in your X factor. X is equal to number of moles of divalent times 2, number of moles of monovalent times 1, number of moles of divalent times 3. Just trivalent to 3, mono to. So simple that way. So we have gotten the number of moles of silver. Then to continue.
Hi, my name is Cheryl.
And I'm Jennifer.
Guess what? There's a channel called MAJESTIC Easy Word Science.
And you know the best part? It makes science so easy. Wow.
It makes science easy, simplified, and very, very fun.
Guess what? Rocket science ain't rocket science anymore.
It's now ABC.
Like if you did science your entire life.
Another thing about MAJESTIC Easy Word Science channel is that he makes available laboratory equipment and reagents.
Guess the best part? If chemistry has been hard for you, he does tutorials.
And another thing is, when you order for these things, they are high quality and they are also cheap and affordable for anybody.
If you want to order, just look at the number below the screen.
And don't forget to subscribe and hit the little notification button down below.
Don't forget to share, of course, obviously there's love in sharing.
Thank you! We'll see you there.
Okay, so since you have gotten that 0.8 watts moles of silver will be deposited by the same quantity of electricity that gave you 0.4 moles of copper, then they said mass. You now use N is equal to mass over molar mass, meaning moles is equal to mass given or giving mass all over molar mass. Molar mass of silver is in bracket 108. So what will it be? Moles is equal to, that's the mass you are asked to calculate for. They don't give you any mass, divide by the molar mass, which is 108. And you have discovered that your mole is 0.8. Then your job is to make this subject to the formula such that the mass given or reacting mass is equal to 0.8 times 108. So what do we have? 0.8 times 108.
86.4.
Okay, we have 86.4 grams. So that is the answer. Think the method is working? Use our X factor. Let me give you another example, but to explain this further, a given quantity of electricity discharged 0.4 moles. This is where your interest lies. If this mole is a mass, I have to change it back to mole before obeying this X factor. Because when I started, I only varied mole and charge, not mass and charge. So if you are giving mass, go back to mole before you get your answer correctly. Okay, so 0.4 moles of copper, then they say calculate the mass of silver that will be discharged by the same quantity of electricity They will give you this in bracket. So very simple. This copper being 63.5 is no more needed because this was given in mole. Assuming it was given in mass, we will use this to convert it to mole by using N is equal to M over Mn. Now, watch very well here. You just discover the one they give to you. They compare two elements, copper and silver. Which one was given? They gave us copper. And how many moles of copper was given? You write it out, which is 4 moles of copper. 0.4 moles of copper. Then go to our X factor formula. Copper is plus 2. Just say X is equal to number of moles of divalent times 2. Then you make it, by doing that, you see that number of moles of copper is 0.4 times 2, you got 0.8. Then the one you are asked to calculate for is silver. And what's the charge on silver? Plus 1. Go to our X factor for plus 1. Still do it. X is equal to monovalent times 1 because of the plus 1. Then our X is what we solve here, which is 0.8. You make monovalent the subject of the formula by dividing both sides by 1 and 1, and you have 0.8. Then you convert that 0.8 from mole to mass. Why? Because they say the mass of silver. Let's assume they ask the number of moles of silver. You stop at 0.8. Now we take another example. Remember to ask your questions in the comments box anywhere you are confused. Majestic students are students of 90% and above, because this is the easy world of science. We make things easy for you. But don't forget to support this channel the much you can. There are many things you are lacking behind. I have the intention of building a greater research institute. Some of you want to follow me up in terms of research, but we have limited resources to do that. So you can support us the much you can. You see the number there on the screen. To get your support, it is okay. Spread the light, please. Let Africa attain a higher level for science, not only just for exams. Okay, example 2. You see it there on the screen, although I'll write it out so that it will be easier for me. If you are told to calculate this quantity, a given quantity, or just say, they might even give you the quantity, 10,380 columns. Yeah. You see, 103,800 columns of electricity, discharged 2.7 grams of aluminium. Calculates I, the number of moles of sodium that will be, or let me say number of moles of sodium, okay, that will be discharged II, the mass of copper that will be discharged by the same quantity electricity. So in bracket we have aluminium is 27, sodium is 23, copper is 64 or 63.5. Which one they give you, you use. I take the question again. 103,800 coulomb of electricity discharged 2.7 grams of aluminium. Calculate number of moles of sodium that will be discharged by the same quantity of electricity. The mass of copper that will be discharged by the same quantity of electricity. Solution. In this case, you know how to do it. Remember our X factor, or the majestic X factor, in calculating second Faraday's law of electrolysis. So what we do, first write given, charge, given. Given charge and elements, right? Yes. Which one was given in the question? Aluminium. That is plus 3. Then what was given about aluminium? 2.7 grams. Remember, is grams. And as far as second law is concerned, you cannot work with this gram. You have to convert it to mole, because that's what the law states, not mass. Rather, it says number of moles is inversely proportional to charge. So we have to convert this to mole. By so doing, we have that N is equal to mass over molar mass. What is our mass? Give you 2.7 over 27, which will give you 0.1. So 0.1 moles of what? Aluminium was provided. Then question I, that's the first question. They say number of moles of sodium. What's the charge on sodium, class? The charge on sodium is plus 1. Then you go to our X factor, which says that X is equal to monovalent times 1. And if you do that, you find out that your X will still be the charge of monovalent. We don't know what X is, you just say monovalent times moles of monovalent times 1. So in this case, okay. We will start from the given. Yeah, that's correct. This is aluminium. That's the mole. So we go here. Exactly. It means that we will start with that of aluminium before we can get our X factor. So to get our X factor, please let's clean this and get our X factor. To get our X factor, in this case, the moles of aluminium that was given, the aluminium is plus 3, so we use this. X is equal to, remember, the number of moles of trivalent, which was 0.1, because that is it, times 3. That's how to get your X factor. Such that our X now is equal to 0.3 moles. So the X factor in this case is 0.3. Then you go back to your question I, number of moles of sodium. So please, if this is given to you, you have to find your X factor. And the other first question, yeah, I did it. So in this case, you now go for sodium, number of moles of sodium. The charge on sodium is plus 1. You use that X is equal to, which is what we have gotten, is our X. 0.3, our X factor, maybe to make it specific, XF here is equal to 0.3 times 1, which will still remain 0.3. So it means that 0.3 moles of sodium will be discharged, and that's your final answer. So the number of moles of sodium discharged is 0.3 moles. Answer. Then the next one says the mass of copper discharged. The mass of copper discharged. The mass of copper discharged, II. Mass of copper discharged. Go back to our X factor. Copper is what? Plus 2. Then X is equal to divalent times 2. Our X has been gotten as 0.3, which is equal to divalent, which we don't know. That's moles of divalent is unknown, times 2. So to make it, to get moles of divalent, we divide both sides by 2. So that what we have now is moles of divalent is equal to 0.3 divided by 2. So what do we have? 0.3 divided by 2. Okay, then 0.15 moles of copper. Then convert the mole to mass, because the question says mass. So what do? You just say that N is equal to mass over molar mass. Let me use small letter, capital letter for reacting mass, and here is for molar mass. So the molar mass of copper is given as 64, and our mole is 0.15, that's our N, is equal to small m, we don't know, all over 64. Therefore, the mass discharged should be 64 times 0.15. What do you have here?
9.6.
Okay, 9.6 grams. So, the quantity of electricity that discharged 2.7 grams of silver will discharge 9.6 grams of copper. Remember, this question might come in form of telling you if $2 is the cost of producing 2.7 grams of aluminium, they might tell you what mass of copper will be produced by the same $2. So in that case, they are now using dollar to replace quantity. Since it's the same thing, it is stating about second Faraday's law, because if you consume more quantity, it means you take more cost. So if you consume the same quantity, it means the cost is the same, provided that the cost of electrolytics and the components of the electrolytes, the electrodes are constant. So don't get threatened when questions comes about second Faraday law of electrolysis. Remember, this is the easy world of science. And don't forget that X factor. And try your ability now. As you are watching me, let's assume we are told if 27 moles, if there are 27 moles of sodium discharged, can you predict the number of moles of aluminium that will be discharged? Yes. Remember that sodium is +1, and 27 of it is our X factor, because the number of moles, or the number of moles for the monovalent is directly the X factor. But if not given to you, you substitute to that. Then aluminium is +3. Just take the inverse. 1/3 times that 27 will give you the number. So if 27 moles of sodium is discharged, 9 moles, if I'm correct, of aluminium will also be discharged, because 27 divided by 3 will give you what? 9. So that is it for this second Faraday law of electrolysis. So this rule is actually, you can verify this when I will still work on electrolysis. You see it. You verify this by connecting 2 or 3 electrolytic cells in series and then subjecting them to the same source of current. In that case, and allowing it to flow at a certain time, in that case, we are supplying the same quantity, passing through the different electrolytes, and that's what Faraday's second law is talking about. So thank you. God bless you. This is the easy world of science. We are going nowhere without your love. So give thumbs up to this video and share this video with your friends and families. Spread the light, expand the easy world of science, then book for your own private classes. I produce excellent and majestic stuffs like you. I want to make you majestic. God bless you so much. You see the number there on the screen.
This 2:30 hot afternoon. This was gotten around 11. Is not properly bleached, so I was gotten by 6 a.m. in the morning. And over here is my iodine solution. So with the dropper, I'll pick iodine, then add separately to each of them. The leaves detached around 2:30 turned dark blue-black, showing enough starch present. Then this one peaked around 11, also turned blue-black, but not as the other one. Then this one peaked around 6 a.m. remained unchanged. The reddish-brown color of the iodine was absorbed by the leaves, but the leaves did not turn. I love you. Thank you for watching.
And